Okay, so moving on to the first part of our lab, we're going to focus on the right hand side of this diagram, so our system model. So we have our system, we're going to model it, and we have our system model, and this is what we're going to be checking our temporal formulas against to see if they are satisfied. So in this lab we will focus on label transition systems and crypto structures. A KTS, a crypto transition system, is basically just a crypto structure and a label transition system joined together. So if you know the basics of an LTS and a KS, a label transition system and a crypto structure, you will know a KTS. So let's start with a label transition system. So a label transition system consists of a four tuple. So it consists of states, denoted by S, initial states, denoted by I, actions, which are a set of actions, and we will go through what these mean in a minute, and transitions. So S is a set of states. So this is basically all the states of your label transition system. So you can say the size of a label transition system, and let's say we call this transition system T. So this is just to denote what the name of this transition system is. So the size of T is the cardinality of S, so basically the number of states we have. So in our first question we ask, S is a set of states. What are the states in the LTS is of name T? So we have 0, we have 2, we have 1, we have 3, and we have 4. So we have 5 different states. Again, there's 0, 2, 1, 3, and 4. So that is our set of states with a cardinality of 5. Again, these can be named anything you wish, but that is just a set of states we have. I is a set of initial states. So I is where the label transition system will enter when starting. I will always be a subset of your set of states. So I is a subset of S. So essentially if you have an initial state, well, it has to be a state within the transition system itself. You can see it's denoted here by an arrow into the first state, which is 0 here. So I is a set initial state. In this label transition system T, it will be state 0. Now depending on the modeling tool you use, some might have an arrow, some might have a ring or another border around the initial state, or there might be no border, no arrow, and it might be have an atomic proposition dictating that this is the start node. But all label transition systems essentially have an initial state. They have to start somewhere. And will always be a subset of the total number of states. And in cases you may have more than one initial state. You could have 0 and you could have it coming in here at 4, just depending on what type of system you have and behavior of it. So ACT is a set of actions. So this is our third value of our tuple. And the set of actions are the actions that cause us to transition from one state to another. So as you can see in our transition system, we come into 0, and we transition over to 2, and we transition to 1, we transition to 3, transition to 4, or from 3 back to 2, etc. But what is causing us to do these transitions? With a label transition system, we need an action. So when we're in state 0, let's zoom in. When we're in state 0, it is the action of B that allows us to go to state 2. When we're in state 2, the action of A allows us to go to state 3, while the action of B allows us to go to state 1. So this is how we determine where we are transitioning in our LTS. So our action determines where we can transition to. So if you're in state 0 and you get action A, we actually can go nowhere. It's not a valid transition. But if we get a B action, we can go to 2. Again, this is a deterministic label transition system, so this means at every state we have a transition which takes us to another specific state. So if this was non-deterministic, if we were at 2 and let's say we took the action A to go to 3 and also the action A could take us to 1, then it is non-deterministic. We cannot tell if we ran our program on the system which path it would actually take. So that's the difference between deterministic and non-deterministic. Deterministic is you only have one action goes to a specific state. In non-determinism, an action can go to multiple different states, and the behavior of the system is unknown, and you must account for these different behaviors. And the final element of our tuple is the transition itself. So what is a valid transition? Well, we just described it there. Again, it is a subset of we have a state, we have an action, and it goes to state prime, if you like. So what is a valid transition? We're in state 0, we have action B, and we go to 2, state 2. So that is a valid transition. What is an invalid transition? Again, if you're in state 0 and you go action A and you go to 2, that is not a valid transition, so that is not a subset of this. Oh, and for the record, our action is a set of actions, so our set of actions here is just A and B. Now this A and B can occur multiple times, but these are the actions we have. So we have B, 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 B here, and we have A, and A. So just our set of actions is just A and B. And the transition is a total transition relation, and it's basically from a state, take one of our actions that is part of our set and go to another state. And if it's a valid transition, then it's a subset of this. So let's say we have a state with no outgoing transition. We call it a terminal state. So essentially, if you came to 0, you went to 2, you go to 1, we see we can actually always perform action A in state 1, which will always take us back to 1. Similarly, if we're in state 2, take A, go to 3, take action A, go to 4. Now if we take action B in state 4, we transition back to, again, state 4, and we can continually keep in this loop. We don't actually have any terminating state, because the terminating state has no outgoing transition. Now, let's say we delete this transition. Let's say that no longer exists. So let's highlight it like that. Let's say that that no longer exists. Now, if we take 0, transition B to 2, transition B to 1, this is now a terminating or a terminal state. We have no outgoing transition. This is where the label transition system will end. We cannot go anywhere from here. That is just what a terminal state is. Now an execution is a sequence of transitions that is either infinite, such as 0, goes to 2, goes to 1, goes to 1, goes to 1, goes to 1 forever. 0 goes to 2, goes to 3, goes back to 2, goes to 3, goes back to 2, and does that forever. Or 0 goes to 2, goes to 3, goes to 4, and that goes to 4 forever. So that is a valid execution on a label transition system. So that is what we mean by infinite. Or it is finite, ending in a terminal state. So once more, if we cancel this transition, then we can have a finite transition. So if we can go from 0, transition to 2, transition to 1. Because this is a terminal state, this is a valid execution. That's what I mean by an execution is a sequence of transitions. And in the sequence we can actually determine what states we traverse to. So that is labeled transition systems.